We're going to learn how computers work in this video, and this is great knowledge for anybody. It's good to understand the fundamentals of how computers work, but it's particularly important knowledge if you're already a programmer or are becoming a programmer, and particularly if you're learning this programming language called the Go programming language, which is the best programming language in the whole world, in my humble opinion. So here's the game plan of what we're going to learn in this video. We're going to learn about how computers work. And the takeaways are right there. So you're going to learn the fundamentals of how computers work. In like 10 minutes, you'll understand the fundamental premise of how computers work. And then after this video, I'm going to do a video on numeral systems where we're going to learn all about the decimal numeral system, the binary numeral system, and the hexadecimal numeral system. So that video is coming after this one. This is going to be a playlist of just establishing some fundamentals that are really good to know about computers. And in this next video, you'll learn why 2A and 038F are such cool hexadecimal numbers. I saw this one on the back of a car, and you'll understand what kind of car it was after you watch this video. And then we're going to see about measuring bits and bitwise operations. So when we get into that, we're going to look at some Go code, and we'll look at bit shifting, like right here, we're shifting bits over. And then we'll also look at Iota, which is a Go language programming idiom. And Iota is also, interestingly, the smallest letter in the Greek alphabet. So it's like, give me one little thing, give me one thing. So A would be 0, B would be 1, and then 2, 3, 4, 5. It just goes up one little thing at a time, just one at a time. So that's a programming kind of mechanic that you could use, an idiom that you could use in the Go language. And then in that video, we'll also see how to use bit shifting and Iota. So here we're bit shifting and using Iota to calculate measuring bits: kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, yottabyte. Starts getting up there. It's like, oh yeah, what do those stand for? So that'll be the third video in this playlist. It's just a preview of the playlist. And then we'll learn about text, because text is also really important in coding schemes, right? You're going to learn about coding schemes in this video. But we'll learn about ASCII and Unicode and UTF-8 and what those are. And again, this is really important if you're any type of a programmer, but particularly if you're a Go programmer, it's really important. And then after that, the next video after that in this playlist will be the palindrome challenge. In that video, which is going to be awesome. I'll tell you about it in that video, but it's going to be awesome. All right, so here's how computers work. These are the primary takeaways. But I don't want you to look at that for a second, just look at me. And so here's how computers work. And this is the analogy, and it's a beautiful analogy, but computers are like a porch light on Halloween. Okay, so porch light, this light switch, in America we have, and maybe in other countries, there's this, I don't know, is it a holiday or is it a festival? There's this day, October 31st, where kids dress up in costumes. And they go trick-or-treating, which means they go to their neighbors' homes and they have a little bag. And if the porch light is on, that means come trick-or-treat here. And if the porch light is off, that means don't come to this house. So if the porch light's on, kids go up, they ring the doorbell, and they get candy. Well, that's a beautiful analogy right there for how computers work. Okay, so here it is. We're going to break it down. But that light switch on the porch, that light switch, if it's in one state, it means one thing. And if it's in another state, it means something else. So with one light switch, we are encoding two messages. If that light switch is on, that means come trick or treat. And if that light switch is off, that means go away. And so with one light switch, we've stored information and we've conveyed information, and the information is conveyed because we're using a coding scheme. And there's this coding scheme that everybody knows that on October 31st, on Halloween, if the porch light is on, if that light switch, if that circuit, right, if that's on, that means come trick or treat. That's the coding scheme. And if it's off, that means go away, right? So one switch, one circuit is storing and conveying two different messages: on, trick or treat, off, go away. And that's really how computers work, because computers run on electricity. And electricity has two discrete states, on and off. And depending upon those states, we could store and convey two messages. So if we have one light switch, one circuit, one switch, one transistor, those words are all interchangeable, right? We could store some kind of a coding scheme. And so here, if that light switch, if that switch is on, it means come away. If it's off, go away. So here's a question for you. If we had two lights, how many messages could be stored and conveyed? With two lights, we could store 4 messages because they could both be off, they could both be on. then we could have this combination of off on, and we could have that combination of off on. And so we could give our friends this coding scheme, and then like maybe we're in college and our friends walk by our house and they see our 2 porch lights and they have the coding scheme and they pull it out and they look at the paper and they're like, hey, both porch lights are on. That means bring beer or whatever, right? And if we had 3 lights, how many messages could we store and convey? If we had 3 lights on our porch, 3 switches that could be in different configurations of on and off, how many messages could be conveyed? That's 8. Right? That's 8. And so we could have this combination of off, 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 or on, or any combination, these 8 combinations of ons and offs, and then we could create a bigger coding scheme, right? And so instead of writing all this off and on, let's just write 0 for off and 1 for on. Oh, right? And instead of like having, you know, all of that mess there where we see both the 0s and 1s and the off and ons, let's just write the 0s and 1s. And so now this starts to look like computer stuff, right? With the 0s and 1s. And if you've ever like computer image, right? 0, 1, 0s and 1s, right? If you've ever Googled, like you've seen these things, right? Like computers often will have these images where there's a bunch of zeros and none are coming up. Computers, let's do this. Fix that search is kind of a wacky search. Computers, 0s and 1s. So 0s and 1s there. And I don't know, 0s and 1s here, right? And 0s and 1s there. So, right, like this thing about computers and 0s and 1s. So the 0s mean off and the 1s mean on. And so instead of having some goofy coding scheme, we could start to associate these 0s and 1s with on and off. And instead of using a switch, a light switch that's on somebody's porch, we'll just have these little switches inside the computer, right? And we could call them switches, or we could call them circuits, or we could call them transistors. But these switches, circuits, transistors, and all those words could be used interchangeably. They could be in on-off states and they could be checked. And so if we have 3 of them in an off state, right, we could store 3 off states, 3 circuits, 3 switches, 3 transistors in an off state, and we could just randomly say that means the capital letter A. And if 3 of them are in an on state, we could say that randomly means a capital letter H, right? And so if we came up with this coding scheme here, where we had, here's our coding scheme over on the left, and we had this series of 0s and 1s over on the right, like what would that translate to? So this 0, 0, 0, the 0, 0, 1 right there, that would be a B, right? And then this would be an A, and then that would be a D, and a C, and an A, and a B. And so we could start to have circuits, switches, transistors, and on-off states, and those on-off states could be encoded to mean something. And so that's how computers work. It's like the porch on Halloween. If there's a circuit in an on state, then that means something. And if there's a circuit switch in an off state, it means something else. And then we could start to have multiple switches, multiple circuits in on-off states, and we could associate them with meanings, with letters, with colors, with sounds, right? Like if they're in this state of on and off, it will represent this color or this sound. And then each little picture element, each pixel on your screen could have a color associated with it. And when we have tons and tons of pixels, it could start to make an image. And so that's like amazing, but it's like all of these 0s and 1s, all these circuits, all these switches in on-off states, which are represented as 0s and 1s, and that ultimately can be an image on a screen, because each of the little dots of a picture element of a pixel is a certain color, and each color is stored, that information of that color is stored as 0s and 1s, or circuits in on-off states. Just like the porch on Halloween. If you remember that computers are like a porch light on Halloween, you know how computers work, all right? And so the next thing that I wanted to say about that was, binary digits. That's what I wanted to say next. So we have those 0s and 1s, and computers can have a circuit, switch, transistor in an off state or in an on state. And so we represent the off as 0, the on as 1, and that's 2 different states, or 2 digits, and so they call those binary digits. Bi is in like bicycle or biplane. Bi means 2, and we're talking about 2 binary digits. And binary digits, we abbreviate that as bits. And so we could measure bits, and we could have like a single bit, which is a single 0 or 1, a single off or on, 0 or 1, and we could have 8 bits, which we just call a byte. Because originally computers worked with 8 bits and they called it a byte for whatever reason. And then we could have 1,024 bytes, and that's called a kilobyte, because a kilo is like 1,000. And then we could have like 1,024 kilobytes, and that's a megabyte. And we could have 1,024 megabytes, and that's a gigabyte. And we could have 1,024 gigabytes, and that's a terabyte. And so computers are working with these binary digits or these bits, and we can measure the bits like that. And so a useful thing to know about all this is like you can figure out how many messages can be stored by this formula 2 to the power of n. So if you have one switch, one light switch or one switch, one circuit, one transistor, you could store two things. Off, it means go away. On, it means come trick or treat. Two lights, we could store four things, and we saw that. Three lights, we could store eight things, and so that formula is 2 to the power of n. And so if we had 8 lights, we could do 256 things. And if we had 32 circuits, switches, transistors, call it what you will, right, we could store 4,294,967, 290, all of that. 4,294,967,296 different things could be stored if we're working with 32 switches, circuits, transistors that could be in different configurations of on and off. We could store that 4.2 billion different things right there. So here's a little disambiguation between circuits, switches, transistors, and gates. So you can pause the video and read that. And that's pretty much the fundamentals of how computers work. I'm just scrolling through here. It's, oh, you got to see this. You got to see this. Look at that right there. So this is the power switch. The power switch turns the computer on and off, and it's a beautiful graphic design because the power switch is a combination of the 0 right there, and the 1, which means 0's off and 1's on. So the on-off button is symbolically representing 0 and 1, which stands for on and off, which is pretty extraordinary. And ultimately, computers operate with on-off states, which we abbreviate as humans as 0s and 1s, and we call that machine language. And so there's machine language, and then assembly language, and then above that, we have procedural programming languages. So we write programs in this third generation language, procedural programming languages, and then we compile them or translate them down to machine language to run on the machine. And so that's kind of interesting to know also about machine language. All right, so that's a little bit about all that. I will say here's Gordon Moore. He had Moore's Law, and Moore's Law said that every 18 to 20 months, the number of switches or circuits or transistors that were on a silicon wafer integrated circuit chip would double, right, every 18 to 20 months. And so back in the 1970s, there was like 4,000 circuits on a silicon wafer, which was the size of your thumbnail, even thinner. And today there's 50 billion on something the size of your thumbnail, 50 billion little switches that could be in some on-off state, and it could be checked. There's 50 billion of them, and it's on something about the size of your fingernail, right? Like, that's extraordinary. All right, so that's a little bit about how computers work. We learned about circuits and switches, coding schemes, right? A coding scheme is like this idea here that on-off states could mean something. So we learned about circuits and switches, right? Like a switch can be in an on-off state, like a porch light on Halloween. We learned about binary digits. So we represent the on-off states as 1 for on, 0 for off. And a binary digit is, one of those zeros or ones. And 2 to the power of n tells us how many, like if we have 8, it's 2, 4, 8, 16, 32, 64, 128, 256, right? 256 different things with 2 to the power of 8 that we could store. And so that formula there tells us how many different combinations of on-off we have, depending upon how many different switches we have. And we didn't learn about the 5 generations of computers, but we learned about bits, bytes, kilobytes, megabytes, gigabytes, terabytes, and we also learned about machine language. All right, so if you want to check out these next videos in this playlist, make sure you hit that subscribe button, and then you'll be notified when these next videos come out. And also hit that like button and comment down below, because that actually motivates me to sit down and make these videos. It takes a little bit of time to make them, but I also really enjoy sharing this knowledge with other people. But it's motivating. It motivates me to do it when I'm like, wow, okay, a lot of people liked this and commented, and then it motivates me to make more videos. So hit that like button, and I'll make some more videos. But I'm definitely making these, so subscribe if you want to check them out. All right, see you next time.